Section 9.7 of your textbook explains the concept of a function. A function is a relation that assigns to each member of one set, called the domain, exactly one member of another set, called the range. A member of the domain is called an input or an argument of the function, while a member of the range is called an output or a value of the function. An argument that produces a value of 0 is called a zero of the function. Now, an illustration that's commonly used to describe the idea of a function is that of a black box or a machine. And if we think of the function in this way, as a machine, we can think of it taking in an input and performing some operations on it in order to produce an output. The reason this illustration is helpful is because it highlights the key aspect of the definition of a function, which is that each input is paired with exactly one output. The function performs its operations in a specific and consistent way so that every time that same input goes into the function, the same output comes out of the function. It's impossible for the function to take in the same input and produce two different outputs as a result. It is possible for the function to produce the same output from two different endpoints, and we'll see some examples of that later. Functions can be represented by mapping diagrams, sets of ordered pairs, formulas, and graphs. So let's look at some examples of that. First, let's consider a mapping diagram. In the diagram shown, we have the members of the domain on the left-hand column and the members of the range in the right-hand column. And the arrows are indicating the function process, whereby a member of the domain is assigned a member of the range. So for example, the argument 0 is paired with the value 0. The argument 1 is paired with the value 1. The argument -1 is also paired with the value 1. And remember, that's possible for a function. We can have two different arguments that get paired with the same value. We can't have the reverse. We can't have two different values paired up with the same argument. The idea of a mapping diagram and the information that it communicates can also be expressed more concisely through a set of ordered pairs, in which the first number in the ordered pair represents the argument of the function, and the second number in the ordered pair represents the value. So that ordered pair 0, 0 is indicating that the value 0 is assigned to the argument 0, just as we saw in the mapping diagram. In the same way, an argument of -1 leads to a value of 1. For this function, an argument of 2 leads to a value of 4, and etc. A third way to represent a function is through a formula, such as the formula y equals x squared shown here. In this formula, the x variable represents the argument of the function, and the y variable represents the value of the function. So we can see, again, that an argument, such as x equals 2, is paired by the function with a value, y equals 4. The argument -2 is also paired with that same value of 4. Finally, it's possible to represent a function through a graph. The graph shown here is the graph of that same formula, y equals x squared. And once again, we can see the same information being communicated in a different way. We have ordered pairs on the parabola, and each ordered pair is indicating an argument and a value for this function. So the argument x equals 2 is paired with the value y equals 4. And the graph shows many other ordered pairs that are produced by this function. Now, there are relations that are not functions. So let's look at some examples of how we can identify those relationships as well. First, look at the mapping diagram. Once again, the arguments from the domain are on the left-hand side, and the values from the range are on the right-hand side. We can see that the argument of 1 is associated with a value of 2, and the argument 2 also has that same value of 2, which again is not a problem for a function. However, look at the argument 3. In this case, this one argument has two different values that it's paired with, both 3 and 5. So same argument, two different values means that this relationship is not a function. How about the set of ordered pairs shown below? Well, we can see immediately that there are several ordered pairs that contain that same value, 0, even though they have different arguments. That's not a problem for a function. But if we look at the second ordered pair and the fourth ordered pair, we see that both of them have the same argument of 5, but they have different values. The first ordered pair, we see the value is 0, and the second ordered pair, the value is -3. Since that same argument is paired with two different values, we would say, no, this relationship is not a function. What about the formula y squared equals x? Once again, remember that x is representing an argument. So let's take the example of 4 as the argument. There are two possible values then for the function, because 2 squared equals 4, but -2 squared also equals 4. So the argument 4 could be assigned to the value 2 or to the value -2. And since we have the same argument and different values, no, this formula does not represent a function. Finally, look at the graph, and we can see the same problem arising. Take, for example, the argument x equals 4, and notice that there are two associated values for the argument 4. We have 4, 2 and 4, -2, both appearing on our graph. Therefore, no, this relation is not a function. Lastly, let's consider function notation, which is a way of presenting the arguments and the values of a function together in a clear and concise way. The notation f of x denotes the value that is paired with the input x by the function f. So let's look at some examples of this. F of x equals 2x plus 3 is an example of a function, and we're going to find different values of that function. First, let's find the value f of 4. And remember, what this means is we're looking for the value of the function when the input, or the argument, is 4. In order to find that, we simply substitute 4 in place of x in our function formula and perform the operations. This leads us to the statement that f of 4 equals 11. What it's indicating is that for an argument 4, the function produces a value of 11. What about f of -5? We can calculate that in exactly the same way. And we see that f of -5 is -7. The argument -5 produces a value of -7. Finally, how about f of 0? Once again, we simply replace x with 0 in our formula, and we see that f of 0 equals 3. That means that our function assigns a value of 3 to the argument 0. Let's look at a different function. G of t equals 6t squared minus t. It's fairly straightforward to find each of these following values from that function. G of 1 would be 6 times 1 squared minus 1, which means that g of 1 is 5. G of -1 would be 6 times -1 squared minus -1, which would be 6 plus 1. So g of -1 is 7. And then finally, g of 0 would be 6 times 0 squared minus 0. So g of 0 is 0. There's a value of 0 when the argument is 0. And remember that a 0 of a function is a number that produces a value of 0. So in this case, we would say that the 0 of this function is x equals 0.